Welcome back to our ongoing deep dive into the fascinating world of the OEIS. We're exploring this vast collection of integer sequences.
One intriguing number pattern at a time.
Exactly.
Yeah.
And today, we're going to tackle A000000.
Yeah. A000000.
A sequence that might seem unassuming
At
first glance, yeah.
But trust me, it's deeply connected to some pretty fundamental concepts in number theory.
Oh, absolutely.
Combinatorics.
So for our listeners who might need a quick refresher, what exactly is a partition? I'm sure a lot of people listening are familiar, but it's always good to lay that foundation.
Absolutely. A partition of a number is basically just a way to represent it as a sum of positive integers.
Okay.
For example, let's just take the number 4.
Okay.
We could express it as, well, 4
Right.
is 3 plus 1, 2 plus 2,
Yeah.
2 plus 1 plus 1, or even 1 plus 1 plus 1 plus 1.
Right.
Each of those combinations is a distinct partition of 4.
Okay, so how does this tie into A000000 specifically? I'm looking at the sequence now, 1, 2, 4, 7, 12.
Right.
What's the pattern connecting these numbers back to those partitions?
So the pattern lies in the number of partitions.
Okay.
The nth term in A000007, which we denote as A of n,
Okay.
represents the total number of partitions for all the integers from 0 up to n. So for instance, a A of 4 would be the count of all partitions of 0.
Okay.
1, 2, 3, and 4
Gotcha.
combined.
Okay, I see. So as we move further down the sequence,
Yeah.
it's not just about the individual partitions,
Right.
but rather the cumulative count of all the ways we can break down the
Exact data.
increasing numbers.
Yeah.
That's pretty neat,
It is.
but I have a feeling this is just the beginning.
Oh, this is definitely just the tip of the iceberg.
Yeah. The OEIS entry hints at some surprising connections that go beyond simply counting partitions.
Absolutely. So A000070 isn't just about the total number of partitions. It also kind of encodes information about the specific integers used within those partitions. For example, it also counts the total number of different integers
Okay.
used across all the partitions of n plus 1.
Okay. That sounds intriguing.
Yeah.
Can you illustrate that with an example, though?
Sure.
Just to make sure I'm grasping the concept?
Of course. Let's stick with n equals 3,
Okay.
which means we're examining the partitions of 4.
Okay.
We have 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1.
Yes.
If we list out all the integers present across these partitions, we get 1, 2, 3, and 4.
Okay.
That's a total of 4 distinct integers.
Right.
Now here's the key. Even if a number appears multiple times within a single partition, we only count it once.
Okay.
So despite one appearing 4 times in the partition 1 plus 1 plus 1 plus 1,
Yeah.
it only contributes once to our final count.
Gotcha.
And if you check the sequence, AA of 3, which is the 4th term, is indeed 7.
That's fascinating. It's like this sequence is revealing a hidden structure
Yeah.
within the seemingly simple act of partitioning numbers.
It is. It's really interesting.
And there's even more to uncover.
Oh, yeah.
I noticed a comment in the OEIS entry
Yeah.
that mentions a connection to something called Ferrers diagrams,
Right.
which sounds very visually compelling.
They are. Ferrers diagrams offer a really elegant way to actually visualize partitions.
Oh.
Imagine representing each number in a partition as a row of dots with the rows arranged in descending order of length.
Oh.
So for the partition 4, you'd have a single row of 4 dots.
Right.
For 3 plus 1, you'd have a row of 3 dots above a row of 1 dot,
Gotcha.
and so on. Now, what's fascinating is that if you take the Ferrers diagram for each partition of n and add a new dot, represented by an asterisk, to the end of each row, you essentially generate all the partitions of n plus 1,
Okay.
though with some repetition.
So we're essentially constructing the partitions for the next number
Yes.
by systematically building upon the existing ones.
Exactly.
And the number of ways we can do this is precisely what A000000 is tracking.
Precisely.
Wow.
And this observation about Ferrers diagrams comes from a comment by mathematician John Perry.
Oh, wow.
It's a testament to the collaborative nature of the OEIS.
Yeah.
It's a platform where mathematicians contribute their insights and observations,
Right.
enriching our understanding of these sequences in some really unexpected ways.
That's a fantastic point. The OEIS is clearly more than just a catalog of numbers.
Oh, for sure.
It's a vibrant community.
Yeah,
Where
definitely.
mathematical exploration unfolds.
Absolutely.
And speaking of further exploration, we've only just scratched the surface of A000000.
We have. There's so much more to delve into.
Yeah, there's much more to delve into, including connections to one transitions, and even the world of graph theory.
Oh, yeah.
But for now, we'll take a pause and return in our next segment to uncover these intriguing connections. Stay tuned.
All right.
Welcome back. We've been exploring A00000000 and its connections to partitions and Ferrers diagrams.
Right.
The OEIS entry mentions something called one transitions.
Yes.
What are those?
So one transition
And how do they relate to this sequence?
offer another way to visualize and manipulate partitions.
Okay.
Imagine you have a partition that includes at least one.
Hmm.
A one transition involves removing one of those ones
Okay.
and adding it to another number within that same partition.
So if we had the partition 2 plus 1 plus 1,
Right.
a one transition could involve removing a 1 and adding it to the 2,
Exactly.
resulting in 3 plus 1.
Precisely.
Okay.
And here's an important detail.
Okay.
If you have multiple instances of the same number, they're considered interchangeable. So in our example, 3 plus 1 is equivalent to 1 plus 3.
Right.
The order of the numbers within the partition doesn't affect the outcome of the one transition.
I see. So it's about the overall structure of the partition,
Yeah.
not the specific positions of the individual numbers.
Exact.
Okay. But how does A000000 quantify these one transitions?
So A000000 of n gives us the total number of possible one transitions across all the partitions of n.
Okay.
What's particularly interesting is that these one transitions can be organized into a structure called a poset,
Yeah.
short for partially ordered set.
A poset. That sounds intriguing, but I must admit I'm not familiar with that term.
Sure.
Could you elaborate on what a poset is and how it applies here?
Of course, a poset is a way to represent relationships between elements in a set where not all elements are necessarily comparable.
Yeah.
In the case of partitions and one transitions, we can say one partition is less than another if we can reach the second partition by applying a series of one transitions to the first.
Okay.
For instance, the partition 1 plus 1 plus 1 plus 1 is less than the partition 4 because we can perform 3 consecutive one transitions to transform the former into the latter.
So it's like creating a hierarchy.
Yeah.
Or a family tree of partitions, where some are ancestors of others,
Yeah.
based on these one transitions.
That's a great analogy.
Okay.
It highlights how A000070 reveals not just the number of partitions and one transitions, but also the intricate relationships between them.
Fascinating. And there's yet another fascinating connection to explore.
Yes, there is.
Right. The realm of graph theory.
Exactly. A000070 also counts the number of unlabeled subgraphs of a specific type of graph called an n cycle.
Now, graph theory might be a bit outside the comfort zone for some of our listeners.
Sure.
Perhaps you could provide a brief introduction to graphs and n cycles before we delve into this connection.
Of course, in graph theory, a graph is a visual representation of relationships between objects.
Okay.
It consists of vertices, which are points, connected by edges, which are lines.
Okay.
An n cycle, denoted as C sub n, is a specific type of graph where n vertices are connected in a closed loop.
Okay.
So a 3 cycle, or C sub 3, is simply a triangle.
Right.
A 4 cycle, or C sub 4, is a square, and so on.
So these n cycles are essentially polygons with n sides.
Precisely.
Okay. And how does A000070 relate to these graphical structures?
So A000070 also counts the number of unlabeled subgraphs of the n cycle C sub n.
Okay.
A subgraph is essentially a smaller graph contained within a larger one.
Okay.
For instance, if you remove one of the edges from a triangle, C3, you get a subgraph that's just a line with 2 vertices.
Okay.
Unlabeled means we're only concerned with the overall structure of the subgraph, not the specific arrangement or labeling of the vertices.
So for each n cycle, there's a certain number of ways to create these smaller unlabeled subgraphs within it.
Yes.
And that number is given by A000000.
Exactly. It's a remarkable link between the world of partitions and the visual realm of graphs,
Wow.
further demonstrating the interconnectedness of these mathematical concepts.
That's incredible.
For example, let's take C3, our triangle. There are several possible subgraphs we can create. The triangle itself, subgraphs with 2 connective vertices, subgraphs with 2 disconnected vertices, single vertex subgraphs, and the empty subgraph with no vertices or edges.
Okay.
Counting all these carefully gives us a total of 7, which, as you can verify, matches A00000070 of 3.
It's a testament to the depth and richness
It is.
hidden within this seemingly simple sequence.
Absolutely.
We've explored connections to partitions, Ferrers diagrams, one-transitions, posets, and now graph theory,
That's right.
all stemming from this one sequence.
It's pretty amazing.
It really underscores the power of the OEIS to reveal hidden patterns and connections that might otherwise remain obscured.
Absolutely. A000070 serves as a fantastic example of how exploring individual sequences in the OEIS can lead us down these unexpected paths, revealing this intricate tapestry of mathematical connections that bind these concepts together.
It's a reminder that even in the vast landscape of numbers, there's always more to discover and explore.
There really is.
And on that note, we'll conclude part 2 of our deep dive into A00000000.
Okay.
Join us in the final segment as we wrap up our exploration and consider the broader implications of this fascinating sequence. We've journeyed through a surprisingly diverse landscape of mathematical concepts, from partitions and Ferrers diagrams to one-transitions, posets, and even graph theory, all connected by this single sequence.
Amazing.
A000000.
It is.
As we wrap up our deep dive, I'm curious, what stands out to you as the most significant takeaway from this exploration?
You know, I think for me, it's that profound sense of interconnectedness that A000000 embodies.
Right.
It reveals how these seemingly disparate areas of mathematics, like number theory, combinatorics, and graph theory, are all interwoven in these subtle and elegant ways.
Absolutely.
You know, it's a testament to the inherent unity of mathematics, where exploring one concept can lead to unexpected insights in seemingly unrelated fields.
That unity is truly remarkable.
It is.
Makes me wonder, what are the broader implications of these connections? Why should our listeners, especially those in STEM fields, care about this particular sequence and its hidden depths?
Well, I think it speaks to the importance of embracing a multidisciplinary perspective.
Okay.
A000070 reminds us that the most fascinating discoveries often lie at the intersection of different fields.
That's true.
By venturing beyond our specialized areas and exploring connections with other disciplines, we open ourselves up to new possibilities and a deeper understanding of the underlying principles that govern our world.
It's a reminder that knowledge is not compartmentalized.
No, it's not.
But rather a vast, interconnected network waiting to be explored.
Absolutely.
A000070 serves as a compelling example of how seemingly abstract mathematical concepts can have unexpected implications and applications in a variety of fields.
They do, absolutely.
And let's not forget the role of the OEIS itself.
Right.
More than just a database of sequences.
It is,
It's a vibrant community.
Definitely.
A platform for collaboration and a catalyst for discovery.
Absolutely.
It empowers us to explore this vast landscape of numerical patterns, uncover hidden connections, and push the boundaries of mathematical knowledge.
For sure.
And 000070 is just one example among countless others.
It is.
Waiting to be explored within the OEIS.
There are so many out there.
It's a treasure trove of mathematical gems, each with its own story to tell and secrets to reveal.
Absolutely.
So to our listeners, I encourage you, delve into the OEIS, pick a sequence that intrigues you, and see where it leads.
Have fun.
You never know what unexpected connections and insights you might uncover.
Exactly.
Until our next deep dive.
Sounds good.
Happy exploring.